Hi, my name is Amir Hossein Zamanian from Southern Methodist University. Today I'm going to present identification and compensation of cogging and friction forces in tubular permanent magnet linear motors. Manufacturing industries are demanding faster and more precise loading and positioning systems to meet the growing requirement in productivity and precision. Permanent magnet linear motors are used for precise control of velocity and position in applications such as machine tools, printing, labeling, textile, and semiconductor industries. The advantages of permanent magnet linear motors are they have less friction and backlash forces due to elimination of mechanical transmissions, such as gears, and they have no limitation in velocity except the limitation that are imposed by the encoder's bandwidth, and they have mechanical simplicity and they have longer lifetime. A major disadvantage is that they present a lot of disturbance forces against the desired force, which are not desirable in permanent magnet linear motors. These disturbance forces in PLML can be categorized in mechanical and electromagnetic forces. Mechanical disturbances are inertial forces and friction forces, including viscous friction and Coulomb friction. And electromagnetic disturbance forces are Cogging force, ripple force, and back electromotive force. Cogging force is defined as the tendency of the translator to stay in a specific position. And ripple force is defined as variation of the force factor due to the changes of the coil self-inductance during translator's displacement. I tried to sketch a schematic of permanent magnet linear motors. This is a slotted version of PLML. As we mentioned earlier, one of the main disturbance forces exhibited in a PLML is Cogging force. There are two potential sources of Cogging force. The first one is the interaction between the permanent magnets and armature slots that generate periodic force along the translator motion with a wavelength equal to the slot pitch. And the second one is due to the finite length of the armature or end effects that generates periodic force with the wavelength equal to the pole pitch. A slotless PLML does not have this problem, but they have less thrust force and they are more expensive. Several solutions suggested so far, such as skewing the slots relative to the magnets, optimization of the architecture of the poles and slots, and control of the armature current and generating a counteracting thrust force. In this study, we carried out numerical and experimental studies to identify and compensate the undesired forces produced by PLML to a secondary mechanism. A potential application of this compensator can be seen in biomechanics and human rehabilitation, where the friction forces causes tiredness of the muscle and Cogging forces acts as a disturbance in patient's intentional motion. So we provide a parametric model to be able to estimate the undesired forces, and then we try to identify the parameters in the model by application of spatial fast Fourier transform and least square parameter identification. And at the end, we made experimental evaluation and we utilized this model in a controller and we investigate how much reduction we had. Dynamic model of a PLML can be presented in the following equations. So here, U is the voltage of a PLML terminal, which is equal to R, which is the resistance of the coil in the PLML, times I of T, function of time, and I here is the current, plus L, the self-inductance of the coil in PLML, times DI divided by DT, which is the rate changes of the current, plus KE, which is a coefficient, times X dot. And this KE is called the back electromotive effect coefficients in here. And then the thrust force in the next equation is F of T is equal to KF, which is a factor, times current. And the last equation is mx double dot, which is a mechanical equation, is equal to F of T, which is the thrust force that is generated in the PLML, plus F of E, which is the external force applied to the PLML, minus F of D, which is the disturbance forces. By neglecting the armature self-inductance in comparison to the resistance, specifically in low frequency, we can simplify the first equation as shown in the next equation, which is F of T is equal to KF U of T minus KE X dot, and then substitute substituting this equation to the next equation in dynamic equation, and considering that when we do not apply voltage, or simply when the voltage is zero, we do not expect to see any external forces, we can just simplify the external force model as shown in the last equation on the right. Therefore, since we assume that we are not applying any voltage in the terminal of the linear motor, this force should be zero, and it means that the right hand side of this equation should also be zero. Therefore, to compensate the effect of PLML, undesired forces in PLML, we need to identify the disturbance force Fd in this equation. So the first term of the equation was the inertial effect, and the second term was related to back electromotive force effects. However, the last term Fd is summation of two terms, which is F of S, or friction forces, plus F of C, or Cogging force. We use the Strebeck model to model the viscose and Coulomb friction in PLML, which is F of S is a function of x dot is equal to F1 is a coefficient plus F2 another coefficient plus e to the minus x dot divided by x dot 1 squared times signum of x dot plus cx dot, which comes from viscose friction. Because in many commercial applications we are using optical encoders or any encoders, there are some uncertainties because of the quantization error, and determination of the signum of x dot is not very easy. That's why we defined an observer, which is z dot plus absolute value of x times z is equal to x dot, which is a bounded observer, and it's limited between -1 to 1, to be able to replace this signum of x dot in this equation with this observer. So we just simply replace signum of x dot by z, and we use this observer in our application. There are many literatures that shown that it is possible to estimate the Cogging force based on a truncated Fourier series expansion, and we use that Fourier series expansion in a spatial domain. So by replacing these equations in the previous equation that I showed in the previous slide, we can just simply say that external forces, which should be zero, is function of the states, which is x dot, x double dot, and z, and is equal to mx double dot plus c1 x dot plus the terms that comes from Strebeck effect plus sigma of an sine of 2 pi n divided by lambda, which is the slot pitch, x plus phi of n, which is the corresponding phase in the Fourier series. And we can combine the effects of viscose friction with back electromotive force in our equation, and we can contract this kf ke divided by r plus c and just simply represent it by c1. So the parameters in this equation are unknown, and it should be identified. We had a kind of rough estimation for some of these parameters, such as viscose friction or the mass of the system, and we measured approximately how much is the value of F1, but we didn't have any much information about Cogging force, and we have to use a kind of good initial guess if we want to use a least square optimization for identification of this model. So for identification of the Cogging force, we use the spatial fast Fourier transform. So what we did is simply we got a relationship between the force that we are measuring in a linear motor versus position, and then we try to use fast Fourier transform in spatial domain. And after that, we used this initial guess, and we had several experiments that we measured the force which is applied from the linear motor to a secondary mechanism, and we measured it by a load cell experimentally, and we had this model in here, and so we had the velocity, position, and acceleration as well as z, and we made an objective function which comes from least square optimization, f of experiment minus f of external, which should be ideally 0 squared, should be minimized, and the minimization of this function implies identification or right determination of the unknown values of m, c1, f1, f2, x dot 1, lambda, a1 to a13, and phi1 to phi13 in this equation. So for experimental procedure, we made an experimental setup, which was a disc with adjustable inertia and a brushless DC motor with an optical encoder attached to the disc shaft, and a linear motor which is attached to a disc by a hinge mechanism, and another revolute joint attached PMLM to the structure or the frame. The disc can be controlled by the brushless DC motor, which is independent of the permanent magnet linear motor, so we are free to choose the position of the disc based on our demand using a PID controller, which is geometrically set to determine the position of linear motor. And we had a load cell between the secondary mechanism, which is a disc, and the linear motor translator. Therefore, what we are measuring from the load cell is considered as external force for the linear motor. All of the control purposes has been carried out by an embedded device with analog and digital I/O input-output and FPGA, which in our case was SB Rio 9636 National Instrument. And the real-time implementation of the controllers has been carried out by real-time and FPGA model in LabVIEW 2015, and the numerical optimization has been carried out in MATLAB 2016. Here's another representation of the setup test. We have the disk and we have the load cell here in between the tip of the translator and the revolute joint which is attached to the disk, and this can be controlled based on our demand. And what we are measuring here when the linear motor is off is all undesired forces. We ran the experiment for constant speed and harmonic motion type, which is x1d is 35 millimeters times this function, which is a smoothed triangle wave, and the other one is the harmonic wave. And we ran this experiment in several situations, and what we did later was that we were able to use a spatial moving average to change these time signals to position or spatial signals. So in forward motions and backward motions in constant speed and harmonic motions, we can make a spatial moving average and we can determine the average of these signals. And if we were good in determination or rough estimation of the inertial force and viscous forces, we probably get a good approximation of the Cogging force, which is only a function of position. However, as you may see here, the results are a little bit different in different situations and in forward and backward motions. This is because that our initial guess was not fit enough to be able to determine these Cogging force terms. We made the spatial FFT for constant speed and harmonic motion separately. As you may see here, for different wavelengths, we are able to determine the value of the corresponding value of the amplitude, and the corresponding phases can be calculated also. And there are a minor difference in forward and backward motions. We were not able to catch this effect by 100%, and when we slide the linear motor forward, there was a little bit difference in comparison to the condition that we get it backward. We use this parameter that we calculated in fast Fourier transform in spatial domain, and then we employed least square optimization in MATLAB, and we were able to determine the parameters which were unknown. So we can tune the parameters and we can identify the unknown parameters. In these slides, you can see the measured real force in our experiment for identification purpose, and the identified model as a function of position, velocity, and time. And as you may see, the model is identified properly. After that, we identified this model. We used this model in a compensator in our controller as shown in this block diagram representation. So we ran the experiment again, this time with utilizing the compensator. And what you see here on the left, you have the model and the identified model and the real measured signal. And we run the other experiment as you may see in the right. When we are employing this model as a compensator, we are not expecting to receive any forces. And as you may see on the right, we were able to compensate the effect of the undesired force considerably. This is another representation of the experiment that we made for harmonic motion in this case, and the results is clear that we don't have much undesired force left after using this compensator. In addition, we compared the normalized force signal energy before and after utilizing the compensator, and as you may see, in different cases we had considerable amount of reduction. We also compared noise reduction in a spatial domain as presented in this plot. It should be noted noted that the force reduction in short wavelengths are due to the Cogging force, and in longer wavelength are mostly related to column friction, backlash, and viscous force compensation. In summary, we provide an improved method for identification of disturbance forces in slotted PLML. The model includes Cogging force, back electromotive force, inertia, and friction force in a Strybeck model, and the model were identified by using spatial FFT and least square optimization in two different motions in forward and backward movement. And what we were able to do was that we were able to reduce the amount of force signal energy between 20 decibels to 31 decibels, which is mostly 97% of the undesired force in the PLML. I'll be happy to answer to your question. If you have any question or comments, please leave a comment below and I'll try to answer to your question. There is a related published paper. I put the link in the description of the video. Thank you for your watching.